Hello! In this episode, we will explore data recovery from ZFS file system in TrueNAS 25.04.2.6. We will show you how to analyze the pool structure and recover data from ZVOLs, datasets, and snapshots, as well as from virtual disks and virtual machines. We will cover typical data loss scenarios, specifically array failures, failed system updates, hardware malfunctions, and accidental deletion. All actions will be performed using Hetman RAID Recovery in a Windows environment. However, similar capabilities are also available for Linux and macOS. ZFS Structure. In the ZFS file system, there are three main types of top-level objects: datasets, ZVOLs, and snapshots. Each plays its own role and has its own specific settings. A dataset is the primary file container in a ZFS pool, functioning as a separate file system for storing files and directories. You can mount it directly in the operating system with access via FTP, NFS, iSCSI, SSH, or SMB protocols. The main advantage of a dataset is that you can configure its parameters independently without affecting other parts of the pool. During creation, you set basic properties: the compression algorithm, LZ4, gzip, zstd, lzjb, zle, access mode, case sensitivity, and synchronous write parameters. After creation, almost all settings can be changed at any time without data loss, allowing you to adapt each dataset to your specific tasks. A ZVOL represents a block device, essentially a virtual disk, which, unlike a dataset, does not contain files directly. It provides block space for creating file systems or for connecting as a disk to virtual machines. ZVOLs operate at the block level and provide more stable performance compared to image files. When creating a ZVOL, you specify the logical size, VOL size, and the block size, VOL block size, which both significantly impact performance. To optimize storage, you can enable compression to reduce volume and deduplication to eliminate duplicates. It is also important to enable sparse mode, which allows space in the pool to be allocated only when data is actually written, instead of reserving the entire volume during creation. TrueNAS also allows for the creation of virtual disks in the form of files, instead of ZVOLs. Such image files can be used via iSCSI, however, they do not support sparse mode and occupy the full volume of disk space immediately upon creation. A snapshot is an instant, point-in-time copy of a dataset or ZVOL state. It is created using the copy-on-write mechanism, where new changes are written to new blocks while previous ones remain unchanged. Because of this, a snapshot occupies almost no additional space and allows you to restore a previous state or individual files without affecting current data. Once created, a snapshot is read-only. It can be deleted or used for cloning. Management is performed via the visible and hide parameters for visibility, as well as through snapshot tasks to automate replication and retention regarding transfer and storage duration. In this part of the video, we will examine the process of analyzing and recovering your data with Hetman RAID Recovery. A link to the software is available below the video. Hetman RAID Recovery will assist you in critical situations if your server hardware has failed, if the TrueNAS operating system is malfunctioning due to updates or system crashes, or if the disks in the server have failed. Regardless of the reason for losing access to your data, the program allows you to extract the information and restore it to a separate storage device. To begin the recovery process, you must remove the disks that were part of the pool and connect them to a computer with Hetman RAID Recovery installed. This can be done directly via SATA ports on the motherboard or using external docking stations. If the hardware architecture of your workstation does not allow you to connect all drives simultaneously, the program allows for a combined approach. In a situation where there's a shortage of free ports, the optimal solution is to create virtual images of some of the disks. You can connect several physical drives directly and use exact bit-for-bit copies for the others, mounting them directly within the utility's interface. The program treats such images as full physical devices and automatically uses them to reconstruct the array structure. This method ensures the safety of the original data as further analysis is conducted using virtual copies. Once all pool components are physically connected or mounted as images, Hetman RAID Recovery will automatically read the ZFS metadata and display the assembled array in the main window, providing access for further scanning and file saving. Upon drive recognition, the program analyzes the meta-information and determines your RAID array configuration. The number of disks required for full data recovery depends on the type of configuration you used. In ZFS Stripe, there is no redundancy, so all disks must be present. The absence or damage of even a single drive makes full structure recovery impossible. In such cases, only partial data extraction from available disks is possible. In RAID Z1, one disk failure is allowed. For recovery, it is sufficient to connect all drives except for the one damaged drive. If two or more disks are missing, recovery of the full structure becomes impossible. RAID Z2 allows for the loss of up to 2 disks. The remaining healthy drives are sufficient for correct pool reconstruction, ensuring data recovery even in the event of a double failure. RAID Z3 has the highest level of fault tolerance and allows for the loss of up to 3 disks. If the other drives are healthy, full data recovery is possible even in complex scenarios with multiple failures. Launch Hetman RAID Recovery, and the program will automatically begin scanning all connected devices. The utility reads ZFS service metadata, analyzes the VDEV virtual group configuration, and uses the obtained data to restore the correct model of your pool. In the working window, you will see all detected drives and their parameters. Select the required pool from the list of reconstructed arrays and launch the Fast Scan mode to quickly determine the data structure. Once the scan is complete, the recovered file system with its full hierarchy of directories and files will be displayed in the main window. You will be able to view all datasets, folders, files, ZVOLs, virtual disk files, LUNs, and snapshots. Expand the folders to check the contents and identify the objects needed for recovery. Select the objects you wish to recover and click Recovery. In the next step, specify a folder for saving the data, choosing a separate medium with sufficient free space. This is critical to avoid overwriting the original data on the damaged disks. The program will display the available space on the target medium and the size of the selected files. Confirm the start of the saving process and specify the final path. Click Recovery again to begin copying your data to the chosen drive. The program performs a bit-for-bit copy with integrity verification and shows the operation's progress in real time. Once the copying operation is complete, click Finish. All your recovered data is now available on the chosen medium in its usual form and ready for use. In situations where data recovery is needed due to accidental file deletion, partition formatting, or the deletion of a virtual machine configuration while the ZVOL remains intact, Hetman RAID Recovery provides tools for deep analysis and information retrieval. The program allows you to work with ZFS objects as full-fledged drives, regardless of whether it is an image file or a ZVOL block device. Thanks to support for a wide range of file systems, including NTFS, REFS, VMFS, the EXT family, XFS, BTRFS, FAT, XFAT, APFS, HFS, and Hikvision FS, you can successfully recover data from virtual environments of any complexity. The recovery process begins by launching a fast scan of the pool to find the necessary ZVOL or virtual disk. The object can be mounted directly within the program interface or pre-saved to the computer as an image file for further analysis. Direct mounting saves disk space as it does not require creating additional copies. After mounting, the object appears in the device list as a regular disk, ready for a detailed investigation of its internal contents. The choice of scanning mode for the mounted disk depends on the nature of the data loss. If files were simply deleted, fast scan is sufficient to quickly display the directory hierarchy. In more complex cases, such as formatting or changes to the logical partition structure, it is recommended to use full scan for a thorough search based on signatures. Once the analysis is complete, you can view existing and deleted files, verify their integrity via the preview window, and save the necessary data to a safe, healthy medium. Hetman RAID Recovery allows for the effective recovery of deleted or modified data from ZVOL objects and virtual disks using previously created snapshots. This solution is critical in situations where a full system rollback is impractical due to the risk of losing current changes made after the snapshot was created. It allows you to maintain the current state of the system while simultaneously retrieving only the necessary data. To begin, you must launch Fast Scan mode, after which a special snapshot folder will appear in the pool hierarchy. Within it, snapshots are organized by name and creation date, allowing you to quickly find the required recovery point. By selecting the appropriate snapshot, you gain access to all objects captured at that moment, including datasets and virtual disks. This allows you to simply copy the necessary elements without changing the current working structure of the pool. If saving large ZVOL images to the computer's local disk is impossible due to lack of time or free space, it's advisable to use the function for mounting objects directly within the program's interface. This allows you to work with virtual disks and LUN images as regular drives without pre-exporting them to physical media. Although data processing speed in this mode may be slightly lower, it significantly saves resources and allows you to immediately proceed to a deep file search within guest file systems such as NTFS, ext4, or XFS. Once the desired object is mounted or selected within the snapshot, you can perform standard search and recovery actions. The program will display the contents of the virtual environment, allowing you to mark specific files and folders for saving. Then simply click Recovery and specify the path to a safe medium with sufficient free space. The program will notify you when the copying is complete, after which all data will be ready to use. In cases where data has been deleted directly from the pool and snapshots are absent or have been overwritten, standard metadata analysis becomes ineffective. The specifics of the ZFS file system and the copy-on-write mechanism means that after objects are deleted, the directory tree is often not preserved. However, the data itself remains in the pool blocks, allowing Hetman RAID Recovery to successfully find and retrieve it even in the absence of entries in the allocation table. Reasons for such loss may include the accidental deletion of datasets, ZVOLs, or virtual machines, along with their attached disks. Also critical is the situation of initialization in third-party operating systems, such as Windows or macOS, which leads to the overwriting of original ZFS service information. In such scenarios, the program performs a low-level analysis of the entire disk surface, identifying files and logical structures by their signatures. To recover, you must select the reconstructed array and launch full scan mode. This process requires more time, as the program works directly with data blocks, assembling scattered fragments into whole objects. If the deletion occurred within a virtual machine, a double analysis is applied. First, the ZVOL is restored as a block device, and then its internal file system is scanned for search of guest OS data. After the analysis is complete, detected objects are usually displayed in a single list at the root of the pool. To find the necessary ZVOL or file among thousands of found elements, use the built-in search function. You can filter results by name, date, or file size. If the object name was not preserved in the metadata, the main guide for identifying the virtual disk becomes its volume size. Found files can be recovered directly or mounted as virtual disks for further study of their contents. Before final saving, it's recommended to use the preview function to ensure data integrity. After selecting the required elements, click Recovery and specify the path to a safe medium with sufficient free space. The program will notify you when the copying is complete, after which all data will be ready to use. If this video was useful to you, please subscribe to the Hetman Software channel. Here, we regularly publish practical instructions and analyze real cases regarding work with TrueNAS scale, OpenZFS, and data recovery in various scenarios, from accidental deletion to critical system failures. In the event of additional questions, or if you've encountered your own specific data loss situation, be sure to write about it in the comments. Describe your pool configuration, the type of failure, or the list of deleted objects, and we'll suggest the optimal options for their retrieval. Thank you for watching. May your systems run stably and your data always remain under reliable protection.